In this module, we will be talking about chemical equilibrium, and in this video, we're just going to do some kind of definitions and framing and get everything set up so that you will be able to go through the rest of the module. So when we're talking about equilibrium, the way that I want to start by framing this is what we're going to do is look at a system. And this word system is just a formal term from thermodynamics that we will get into later in the semester, but we don't have to worry about it right now. It just means we're going to look at this reaction under a certain set of conditions. And when we look at that system, it will be in one of two states. So it could be in a state where it's changing. And if you wait long enough, so that's what we're going to do over this arrow, you will get to a state where it's not changing. And this state where it's not changing, we think about, or we term as it being at equilibrium. So in official definition terms, equilibrium is when macroscopic qualities of the reaction don't change. And so the macroscopic qualities that we're talking about are things like color, pressure, or concentration. And things like microscopic qualities, like or even smaller than microscopic, so an individual molecule may undergo the reaction, but we'll have the reaction going back in the other direction, which actually lets us set up a second definition for equilibrium, which is when the rate of the forward reaction is equal to the rate of the reverse reaction. And this is a kinetic-based definition. And you will see this come up a lot depending on the source that you're looking at. Many times kinetics is taught before equilibrium is taught, so these kinetic terms will come up, and we will use them a little bit later. I guess depending on when you see this video, if things haven't been rearranged anymore. If we have done kinetics, this part will make very much sense to you. If we haven't, it just means that your reaction is going to go forward, right? You have reactants and products, but at the same time, your products are turning into reactants at the exact same rate. Okay, so we're going to look at a reaction achieving equilibrium. And the reaction that we're going to look at is 2NO2 gas in equilibrium with, and so we use these fancy arrows that show the reaction going forward, right? I've got that half arrow pointing to the right and backward because I've got the half arrow pointing to the left. And this is in equilibrium with N2O4 gas. So this is telling me, another way to talk about this being able to achieve equilibrium, to say that the reaction is reversible. And then just a reminder, right, this side, these are my reactants, always. When we talked about this in first semester Gen Chem, I said that it would come back and be important, and this is the part where it comes back to be important. And N2O4 is the product. So even when we're looking at the reverse reaction, where N2O4 is turning into 2NO2, it's a product turning into a reactant. So to look at this reaction, I want to look at what are two different experiments. So it's going to be experiment number 1 on the left and experiment number 2 on the right. And in experiment 1, we are going to start with 1 atmosphere of NO2 at 298 K. And look at what happens as this reaction proceeds. So if I start with 1 atmosphere of NO2, which I'm going to put NO2 in green, right? My starting point is here. So as this reaction goes forward, right, my NO2 concentration, well, in this case, the way that we're measuring that is through pressure. My NO2 pressure is going to decrease over time. And we find that at some point it just kind of evens out, right? The actual pressure stops changing. So this is my NO2 in green. And let's do the N2O4 in blue. So under my initial conditions, I don't have N2O4 listed at all. So that means I'm going to start at 0. And what I find is that my N2O4 concentration is going to increase, and then at some point it's going to level off. So this is N2O4. Now, I am completely approximating the ending pressures of these two. So if you're looking at a graph of this exact reaction, my picture might not be perfect in terms of the numbers, but it's going to give us a good enough approximation to use for what we want to talk about here. In experiment 2, I'm going to start with 0.5 atmospheres of N2O4 at 298 K. So my N2O4 is in blue, and I'm going to start with 0.5 atmospheres. So my reaction will move in reverse. So it's going to make some NO2. So my N2O4 pressure will decrease, and then eventually it'll just kind of taper off. So blue is still N2O4. And my NO2 will start at 0 because it's not listed. That pressure is going to increase, and then at some point it'll just kind of even out. So this is my NO2. So the big thing that I want to point out here, right, we have pressures changing over time, but we see that there's a point at which these pressures stop changing. So I've got just kind of a dashed line. I will go back and highlight this so it shows up just a little bit better. Maybe let's highlight it in yellow so it'll stand out. This line right here. So it's right at the point where my pressures kind of even out, and put a star by it. This is the point at which the equilibrium pressure which we can also, I mean, I said the word concentration. We can also call this a concentration. Now it will matter which one specifically we're working with, but we can kind of use them interchangeably because a concentration is just moles in a volume. Well, we know how to calculate that for a gas if we have the ideal gas law, because it's just the pressure divided by RT. So point at which equilibrium pressure or concentration is reached. And we also call this dynamic equilibrium. And the reason that we call it dynamic equilibrium is because the reaction is still happening. It's just that every time two molecules of NO2 turn into one molecule of N2O4, then one molecule of N2O4 turns back into two molecules of NO2. So the reaction is still going backward and forward, but because we're doing it, one or two molecules at a time, this sort of bulk macroscopic property of pressure or concentration overall doesn't change. All right. Now, some reactions, when they get to equilibrium, have more products, and some reactions, when they get to equilibrium, have more reactants. So even though the word equal is in there, it doesn't mean that the amount of products and the amount of reactants are balanced. It just means that the rates are balanced. So some reactions achieve equilibrium, which I'm going to already start abbreviating, with more product, and some with more reactant. So we need a concise way to describe this equilibrium state. And our answer to this question is the KEQ, which is the equilibrium constant. So unfortunately, second semester general chemistry is the semester of the letter K. So we will use, we already used K. We have already used K in this video to represent Kelvin for temperature. Here now, it's the capital K with some kind of subscript to be the equilibrium constant. For right now, it's going to be an EQ to designate that it's equilibrium, but you will see some places drop that subscript, and in a later video and in a later module, we're going to add some other subscripts to designate specific circumstances. All right, here's how we set up an equilibrium constant expression. So it's a ratio of products over reactants. Now, for a specific reaction, and we use this generic one of A plus B, where the lowercase letters are the coefficients and the capital letters are the chemicals. In equilibrium, the products are C and D. The equilibrium constant expression. So when I ask you for an equilibrium constant expression, this is what I'm asking for, is equal to, well, it's products over reactants, but it is the concentration of compound C to the little c power times the concentration of compound D to the little d power divided by concentration of A to the little a times concentration of B to the little b. So this is the expression. Let's put a little highlight box around this that you will need to write for a specific reaction. Now we're going to do some examples, and we'll be talking about some special cases in the next video. Now, this is concentration, right? That's what those brackets mean. So concentration of C, right? We're talking about moles of compound C divided by volume in liters. All right. We'll do pressure in a later video. Although if you only have pressures, you can still calculate concentrations as long as you have a volume. Or if you have moles and volume, you can get to concentration. There's a lot of flexibility here. This expression is specific to concentrations. So what this would look like, and we're even going to do this for a reaction that has all gases in it. So my reaction is going to be the combustion of propane. So C3H8 gas plus 5O2 gas in equilibrium with 3 CO2 gas and 4 H2O gas. The equilibrium constant expression, it's products over reactants, so it's the concentration of CO2, and that coefficient is 3, so I'm going to raise it to the third power, times the concentration of H2O, that coefficient is 4, so this is to the fourth power, divided by concentration of C3H8, coefficient of 1, times the concentration of O2 to the fifth power. Okay, that's the expression. Obviously, this is a constant value under given conditions, so we're going to get a number that is also the equilibrium constant, and we can use that value to tell us information about a reaction. So I'm actually going to pause, get some reactions written down, although, as always, I know you'll just see it and the video will keep blasting through, but I don't want to waste your time watching me write reactions. So the question that I want to look at with the examples below is, what does KEQ tell us about a reaction? So in our first example, it's H2 gas plus Br2 gas in equilibrium with 2 HBr gas. The equilibrium constant is 1 times 10 to the 19th at 298 K. So 1 times 10 to the 19th, that's a huge number, right? Times 10 to the positive 19th, it's a very large number. So let's just note this. This is very large. So when you try to think about what that means, I think the best thing to do is to write the equilibrium constant expression, which is products over reactants. So it would be HBr squared divided by H2 times Br2. All right, so a really, really big number. You get a big number if the numerator of your fraction is bigger than the denominator. So what this large value of an equilibrium constant is telling us is that at equilibrium, I have more product than I do reactant. So more product at equilibrium. Another way that people will describe this is we'll say that it favors the product, or that the reaction is shifted to the right because the products are on the right. And that's it. This is where we're going to stick with kind of a qualitative assessment for the moment. So in my second example, which is N2 plus O2 in equilibrium with 2NO, my equilibrium constant is 4.1 times 10 to the minus 31. That's a very, very small number. So you could probably expect, without doing anything else, that it's the opposite situation of our last example. So, I mean, let's walk through it in the same way. If we look at the equilibrium constant expression, which is NO squared divided by N2 times O2, the way that you get a very small number is if the numerator is smaller than the denominator. So the denominator of my expression must be much bigger than the numerator, and that means that I have more reactant at equilibrium. Or we could say that this reaction favors the reactants. We could say that it is shifted to the left because the reactants are on the left. In general, what I want you to kind of keep in your head, because you can't always pull the equilibrium constant expression and look at this, but you'll find this trend across reactions. If you have a KEQ greater than 1, the products are favored. If you have a KEQ less than 1, the reactants are favored. And just so that we have everything covered, if you're kind of in the middle, right, KEQ is about equal to 1. Well, this is, neither one of them is favored. You have kind of an equal balance going on.